सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
Good morning. Up to now we have been doing a lot of theory. So, what I am going to do is apply that theory and make it a little useful. We have done a few problems, but this lecture will be almost completely looking at calculating capacitance in different situations. Now, let me start out with the simplest capacitor that we already know about. You have two plates, infinitely large, they are separated by a distance d. I ground the bottom plate and I apply a voltage V naught to the top plate. In between the plates I am going to have air. So, that means my dielectric constant is epsilon naught, permeability is mu naught. Now, we have already done the solution to this, but let us do it again. Idea is that the electric field is going to point away from the plate because there is no reason for it to point in any other direction. There are no side walls that are trying to cause forces to come sideways. If I take any point here, for every bit of charge that is here that is trying to make me move this way, there is a corresponding bit of charge here that makes me move this way. So, the net electric field is always downwards. So, if this direction is x, the electric field is Ex. Once I know that, I can apply Gauss's law, and Gauss's law tells me if I put the top surface inside the metal, bottom surface inside the air, it tells me that Ex times area is equal to charge enclosed, which is charge density times again the area. I will call it dA to indicate that it is a small area divided by epsilon naught. And this is how we get that the electric field is equal to sigma over epsilon naught. Now, this same idea can now be done using displacement vector. We have divergence d is equal to rho. So, the same Gaussian cylinder I can draw, and I now have dx times dA is equal to sigma times dA. There is no 1 over epsilon naught, all right. Otherwise, it is a trivial extension of what we have already written. So, I will get dx is equal to sigma. Now, what is important about either of these is that I can draw a cylinder that extends into the region between the two plates. It does not have to be a very thin cylinder, it can be a very long cylinder, because the electric field is always pointing downwards. So, the sloped sides cannot contribute anything. There is no electric field entering, there is no electric field leaving. Similarly, there is no displacement vector entering, there is no displacement vector leaving. So, the only contribution to surface integral E dot ds or surface integral D dot ds is at the bottom plate, and the charge enclosed is coming from where it intersects the surface of the metallic plate. So, we find that the electric field and the displacement vector are constants in this problem, and from that we can write that the voltage drop V naught is equal to minus integral 0 to d of E dot dl. E is downwards, dl is upwards, so the minus sign goes away, and you get it is equal to sigma over epsilon naught times the total height. Because it is a constant vector, it can pull it out of the integral, so only the total height comes out. And finally, the amount of charge q on the plate is equal to sigma times the total area of the plate. These two pieces of information tell me something very interesting. The total charge is proportional to sigma. The voltage on the plate is also proportional to sigma. So, if I divide these two expressions, sigma should go away. Now, if you look at this derivation, even though I got Ex and dx in terms of sigma, I do not know what sigma is. I know what epsilon naught is, I know what d is, I know what the area is, but I do not know what sigma is. By dividing these two equations, I can eliminate this unknown sigma. So, what do I get? Well, what I get is q divided by V naught is equal to sigma a divided by sigma d divided by epsilon naught. Something that is in the denominator of the denominator goes to the numerator, and the sigma cancels. So, epsilon naught a over d. Now, what is important about this is not the derivation. You have done this I do not know how many times in school and college. What is important is, starting with two equations that both depended on an unknown sigma, I have now got a relation between q and V naught that depends only on the device. It depends on epsilon naught, it depends on the size of the plates, it depends on the distance between the plates. It does not depend on the fields themselves, it does not depend on the charge, it does not depend on anything which is dynamic, which depends on circuit conditions. And this quantity that is only a function of device parameters is called capacitance. So, this is a very important concept, and it does not hurt to repeat this as many times as possible. Capacitance is a measure of how much charge is induced on a plate when you put that plate at 1 volt with respect to the ground. So, if I set V naught to 1, then the amount of charge I will induce in coulombs will be the capacitance itself. So, the unit of capacitance should be coulombs per volt directly, but it is given a new unit, the unit is called farad. Now, the farad is such a large number because the coulomb is such a large number. 1 coulomb of charge is huge, and you will never see it in a normal device. So, typical values of capacitance you will see will be ranging from the picofarads to the microfarads. You will you will never see a millifarad, and a farad you can forget. Okay, so this was the simplest kind of experiment, thought experiment we can do, but let us do a slightly more complicated one. I have got a parallel plate capacitor, but inside this parallel plate I have put a dielectric material. So, I have metal, I have air, I have dielectric, air and metal. So, you can see it is a sandwich kind of construction, and forget the side walls, let us assume that it is infinitely large. I would like to solve this problem. Now, if I apply Gauss's law, I can again get the fields in this region, in this region, in this region, and thereby solve the whole problem. Unfortunately, there are induced charges on the dielectric. So, how do I handle this problem? The answer is, instead of using divergence E equals rho over epsilon naught, I will instead use divergence D equals rho. This is free charge, it is a charge that I deliberately put anywhere. This rho includes the charge on the surface of the plates, but it does not include the charge induced on the dielectric. So, if I apply this formula, apply the divergence theorem, it tells me surface integral d dot ds is equal to charge enclosed. Let me call this region 1, this region 2 and this region 3. So, in region 1, that is, my cylinder has its top side in the metal, the bottom side in region 1. Once again, you can argue that the fields will be directly down. So, the side walls will not contribute, top wall is in the metal, so no field. So, the bottom wall is the only thing that matters. So, I get d1 times area is going to be equal to induced charge on the wall times area. So, D is equal to sigma, which means electric field dx Ex is equal to epsilon naught, sorry, sigma over epsilon naught. Is that clear? Now, in region 2, I draw my Gaussian cylinder, and I again look at this, the sloped parts do not contribute, top part is in the metal, bottom part is important. So, d2 times area is equal to the charge enclosed. This is the true charge enclosed, and there is only one place where there is true charge, which is the plate. So, it is sigma dA, which means this is d1x, d2x is equal to sigma, or E2x is equal to sigma over epsilon. Now, here there is a change. The displacement vector was the same, it is the same here and it is the same here, but the electric field has changed. Earlier the electric field was sigma over epsilon naught, now the electric field is sigma over epsilon. The third region d3 dA is equal to sigma dA, same argument, which gives me d3x equals sigma, E3x equals sigma over epsilon naught. Because you see the third region, I am back into air, and therefore, I am back into epsilon naught. So, if I plot this, and I will plot it here, this is D or E and this is x going down. The displacement vector is a constant. So, it is the same at all values of position. But if you look at the electric field, it is some value up to this point and it is that same value here, but in the region where there is dielectric, the electric field is smaller. All right. Now, I have drawn these two lines as overlapping, I should not do that. D is something. So, this is D, this is E. So, the displacement vector is uniform in x, the electric field vector is not uniform in x. But I know what the electric field is, but again I know it only in terms of an unknown charge density. Okay. Can we make use of that? Well, the top plate is at V naught, and I know that V naught is equal to minus integral 0 to d of E dot dl. That is to say, this relation is still true. Potential is related to electric field, it is not related to displacement vector. But I know what the electric field is in terms of this unknown sigma. So, I can write it as, I will draw the picture again. So, this is x equals 0, this is x equals say x naught, x equals x 1, x equals d. So, it is equal to integral 0 to x naught sigma over epsilon naught dx, the two minus signs get cancelled out, plus integral x naught to x 1 sigma over epsilon dx plus integral x 1 to d sigma over epsilon naught dx. So, I am just taking the solution that we have already worked out. The electric field is strong here, weak here, but I do not know its actual strength because I do not know what sigma is, but I know its form as a function of sigma. So, I have put that in. Well, sigma is a constant and I can pull it out. Epsilon naught and epsilon are again constants. So, the integrals are very trivial. So, what do I get? I get sigma over epsilon naught times x naught plus sigma over epsilon times x 1 minus x naught plus sigma over epsilon naught times d minus x 1. So, we now have an expression for total voltage and the expression for charge q is nothing but sigma times area. So, once again I have an expression for voltage, I have an expression for charge, both of them are in terms of an unknown sigma, but I can divide. And what happens if I divide? Q divided by V naught is equal to sigma A divided by sigma times x naught over epsilon naught plus x 1 minus x naught over epsilon plus d minus x 1 over epsilon naught. Again I can cut out the sigmas and you can see that the answer does not depend on sigma anymore. It depends on device parameters because it depends on A, it depends on epsilon, which is the material of this dielectric, which dielectric I put in. It depends on the spacing, on the gap size and on the thickness of the dielectric. All of these are based on how I made this capacitor. It does not depend on what is happening in the rest of the circuit. So, this is a quantity that depends only on the device physics, and therefore, it can be defined independent of anything else, and so again I can define it as a capacitance. Now, it is worth looking at this capacitance and trying to understand it. Supposing I let this x naught go to 0 and x 1 go to d, that is, these gaps go to 0. So, the dielectric fills the entire region. Then x 1 minus x naught is nothing but d, because x 1 is d and x naught is 0. What will I get? I will get epsilon a over d. So, that is a case filled dielectric. So, then I have capacitance is equal to epsilon a over d. Now, you can compare this to the other case, which is the dielectric shrinks to nothing and you are left only with air gap. So, then x 1 is equal to x naught. So, this term goes away, this x naught is equal to x 1. So, these two will cancel. So, you will get back no dielectric, C is equal to epsilon naught a over d. So, you can see this epsilon naught will go to the top. So, you get epsilon naught a over d. So, as you put a dielectric and as you increase the fraction of this gap over which the dielectric is present, it goes from this value to this value. The capacitance increases. And what is capacitance? Capacitance is the amount of charge that is induced on a plate if you apply 1 volt between the plate and ground. So, as you put a dielectric and as you increase the dielectric constant, the amount of stored charge keeps on increasing. Okay. Now, let us try and plot some of the fields. So, this is again the same plot. This is at voltage V naught, this is at ground, this is x equals 0, x equals x 1, sorry, x naught, x equals x 1, x equals d. Now, we had already plotted it. So, we had shown that the electric field looks like this. So, it is low inside, it is high outside. Now, what is actually happening? What is happening is as follows. Overall, you need an average field, so that when you integrate the field from 0 to d, you build up V naught. So, I will put this average field like this. This is the average field you need. Now, when you put a dielectric in the region where the dielectric is present, the field is actually lower than its average value. That is compensated for by having a very high average value, high value outside. So, that is these two regions. But having a high electric field means having a lot of induced charge. So, by putting a large dielectric constant material inside this capacitor and making it fill most of the gap corresponds to something like this. That is, I have got an average that is this much, but that average is made up of very large electric field here and very small electric field in the rest of the region. And I am, by putting this gap as a very small quantity, I am actually creating a very large electric field here, and that is what is giving me a large amount of induced charge and that is what is giving me a large capacitance. If you look at the voltage, however, well, I will plot that this way, 0, this is D, this is x naught, this is x 1. So, the electric field is doing this. What is the voltage doing? The voltage, the slope of the voltage is related to the value of the electric field. So, the voltage grows strongly. Then here the electric field is low. So, the slope is less, and then it shoots up again, and this is what has to be V naught. And finally, what is the displacement vector doing? Well, the displacement vector is not on the same scale, just constant. Now, the advantage of what we have done is that we did not really have to do any hard work trying to understand what is happening at the surface of this dielectric and this surface of the dielectric. We use displacement vector does not see any bound charge, solve the problem as if it was a vacuum capacitor, and came back and calculated all the fields. It was that simple. If you did not have the concept of displacement vector, this would have been a much harder problem. Okay, now let us take slightly different problem. I have a parallel plate capacitor, but I have two dielectrics. Problem is essentially the same. It is that with our approach, it is almost trivial to solve. Let me just plot what we will get. We know that the displacement vector is going to be constant right through, because the only free charge is at the top plate and at the bottom plate. Whatever induced charge there is on this surface, this surface, this surface, and this surface does not show up in D. It will only show up when you look at electric field. So, the displacement vector is constant. We do not know the value of it, but we know it is constant. The electric field, well, the electric field is displacement vector divided by a constant. That constant depends on the material. So, the electric field is going to look like so it is going to have some value. This value is d over epsilon naught. This value is d over epsilon 1, and this value is d over epsilon 2. So, here in this diagram, I am assuming that epsilon 1 is smaller than epsilon 2, and both of them are much larger than epsilon naught. That is why you see a very large voltage, very large field in the air gaps, relatively small field in dielectric 1, and an extremely small field in dielectric 2. So, then how do I calculate this D, or how do I finally solve the problem? Well, I again use V is equal to minus integral E dot dl. So, I have V naught is equal to minus integral E dot dl, which means I have sigma over epsilon naught times all the air gaps. I am just going to add them up. So, if this is 0, this is x naught, this is x 1, this is x 2, x 3, and d. This air gap is x naught minus 0 plus x 2 minus x 1 plus d minus x 3 plus sigma over epsilon 1 epsilon 1 is this region. So, it is x3 minus x2 plus sigma over epsilon 2 x1 minus x0. As usual, q is sigma a. So, I can divide q by V naught and eliminate sigma, and I can get an answer for capacitance. It is identical to what we have already done. By adding a second dielectric, this approach does not make it any more difficult. There is just some extra terms, and not even that many, there is one extra term. So, this problem of solving for capacitance in a one dimensional geometry is made very simple the moment you start using displacement vector. Now, earlier we talked about electric field and stored energy in the electric field. So, we had got an expression that stored energy, which is the work done to set up the field, is equal to 1/2 integral rho phi dV, that is integrate over the volume the charge density times the potential at that point and divide the whole thing by 2. I gave you a derivation of that, and we found that it was equal to 1/2 integral epsilon naught E squared dV. Now, let us look at what happens if you have dielectrics. Now, this formula came from the idea that I have some charge density rho, and this charge density created a potential phi, and if I bring charges from infinity in all directions and build up this charge slowly, the amount of work I have to do at any point is to bring in a small charge d rho is to work against some fraction of this potential phi, and if I integrate all that work, you get 1/2 rho phi. That argument does not depend on whether there is a dielectric or not. The presence of the dielectric will make calculation of Coulomb's law more difficult, but it does not change this argument. So, this is still true. What changes is this expression. This expression is only correct in vacuum. So, let us see what happens when you have a material. I go back to this expression and I say 1/2 volume integral rho phi dV. Now, what is rho? We have an equation that says divergence D is equal to rho. We worked very hard to get this, and you should sort of dream it when you study electromagnetics. This is one of the foundation equations of Maxwell. So, put that in. This becomes 1/2 volume integral divergence of D times phi dV. Now, we would like to do something to this equation. It looks a little too complicated. So, let me just look at this piece. It says del dx del x plus del dy del y plus del dz del z multiplied by phi. Now, this is just a derivative times a function, and I know that del x of f times g is equal to del x of Fg minus F times del G del x. That is, if I take the derivative of a product, it breaks up into being the derivative of the first term multiplied by the second term and the derivative of the second term multiplied by the first term, and I took one of them to the other side, so there is a minus sign. So, I can use that here, and what do I get? I get del del x of dx phi minus dx del phi del x plus similar terms for y and z. Now, this is a vector, dx times phi, dy times phi. So, d phi is a vector and I am taking its divergence. So, this is nothing but divergence of d times phi, whereas this is d dot minus E. Gradient of phi is minus of the electric field. Now, let us see where that takes us. It is exactly the same derivation as we did for the previous case, except now we have a material present. So, I have 1/2 integral rho phi dV is equal to 1/2 integral divergence d phi dV, which is now equal to 1/2 volume integral divergence of d phi minus plus d dot E whole into dV. I actually had minus d dot minus E. So, the two minuses make it a plus. Now, this is an integral over a divergence over a volume. Any integral of a divergence over a volume is a surface integral. So, it becomes half surface integral over the volume d phi dot ds plus 1/2 integral over the volume d dot E dV. Now, what we do with this surface integral depends on what device we have. If we have a capacitor, the surfaces are in fact the metallic plates, and it is not true that phi goes to 0 there. But if we are talking about charges in free space with some materials present, then phi goes to 0. So, we can't actually throw away the surface term anymore. The surface term can be important, but this piece is the piece we commonly associate with energy in the field. This quantity d dot E over 2 is like energy density in the field. So, when you have a dielectric material, you cannot use epsilon E squared, or you cannot use epsilon naught E squared. You have to use d dot E, and what is d dot E? It is epsilon E dot E over 2. So, the stored energy increases due to this factor epsilon. Of course, the problem actually is that you can also write this as or d dot D over 2 epsilon. You can say it increases for fixed E, or it decreases for fixed D, and this is a very important thing. If you manage to keep electric field constant, let me write it down. The statement is so important, needs to be written down. If E held constant, stored energy up with epsilon. If D held constant, stored energy down with epsilon. Now, where does this make a difference? It is actually extremely important because it is used in relays, it is used in many applications. Let me give you an example. Supposing I have a capacitor plate system and I put a block of dielectric, long block, which has a dielectric epsilon. This coordinate, let us call it z, and at this particular point it is at some position z naught. Now, the question is the capacitor exerting a force on this dielectric, and can we controllably exert this force? For example, this dielectric block could be connected to a relay, and by giving an electrical signal I could be exerting a mechanical force. Now, if I want to do that, I need to know what force I am applying here. Now, the way to do that is first of all to understand why there should be a force and then to calculate it. Let us look at that problem. Now, supposing I held my capacitor to some voltage V. Now, I know that if I hold the voltage to some constant, then effectively I am pinning down E, because integral E dl is the voltage. So, I am essentially holding E constant. Now, if I hold E constant, I find stored energy increases with epsilon, which means that by pulling this in, I am going to increase my stored energy. Now, supposing instead of applying a voltage V, I just deposited a certain amount of charge and then disconnected the circuit. So, instead of V, I have a charge Q on the plate. Now, what happens? Moment I talk about charge on the plate, I have divergence D equals Q or equals sigma. Therefore, Q directly implies displacement vector, and if Q is constant, displacement vector is constant. If displacement vector is constant, stored energy drops with epsilon. So, what it means is that the system will try to move in different directions, exactly different directions, because it is trying to minimize energy. So, depending on whether I am holding the voltage constant or the charge constant, it will do exactly opposite things. It is a very important concept. I will work out the detailed solution using method of virtual work, but I will do that later. The main point to understand is, if I apply a voltage condition on the plate, I am saying electric field is constant, and when electric field is constant, epsilon E squared over 2 is constant. Epsilon E squared over 2 describes the stored energy. So, if epsilon increases, stored energy increases. If on the other hand I have stored charge, charge directly talks about displacement vector, it does not care about dielectric constant, and displacement vector is held constant, then stored energy drops with epsilon, and that tells me that if I push it in, the amount of stored energy is dropping. So, these automatically give you an idea of what D'Alembert's method is going to tell you. We will come back to the actual solution later. In fact, it will be a good idea for you to go and revise your applied mechanics course right now, because the method of virtual work you would have learnt in an earlier course, and it is important that you understand that derivation. Okay. Now, I am going to go to a new idea, and it is an important new idea. I am not going to prove it, I am going to only state it. The proof is not very important. The idea is as follows. Supposing I have a cavity. This cavity could be a capacitor, it could be a insulating box, it could be anything, it could be a motor. I have a cavity, and inside this cavity I have some charges. So, I have rho of x, y and z, let us call it r. Now, I know that if I have charges, that the problem I need to solve is del squared phi is equal to rho over epsilon. Now, if I have material properties that are varying inside this cavity, then I need a better equation than this. The equation I will have is the electric field is equal to minus grad phi, the displacement vector D is equal to minus epsilon grad phi, and the divergence of that displacement vector. So, divergence of epsilon grad phi is equal to minus rho. So, this is what is commonly called Poisson's equation. But really this is the more correct equation. But both are essentially the same equation, unless epsilon has some very non-uniform properties, firm properties. But either way, this is an equation I want to solve. Now, if you look at this geometry of this problem, it is a second order operator. For example, it has del squared by del x squared, del squared by del y squared, del squared by del z squared. So, it is a second order differential equation to solve for phi in terms of charge. Now, if you know anything about your second order equations, you know that a second order equation, for example, d squared x dt squared minus kx is equal to 0. That is a second order equation, and we know that the answer for that, well, let me put plus and put k squared to make it look familiar. You know that the answer to that is x is equal to a sin kt plus b cos kt. Now, what is important are these a's and b's. This system, this differential equation actually has two kinds of solutions. It has sin kt and cos kt, and the amount of sin kt or the amount of cos kt does not get decided by this equation. It gets decided by what we call initial conditions. That is, unless we know what x of 0 is and what x dot of 0 is, we can't pin down a and b. So, this is what is called an initial value problem. You have to first solve the differential equation, then you have to put in your knowledge of the starting values. But there is a problem here. Supposing I put this as the x direction and this as the y direction, and out of the board is z. Well, this is the region over which I want to solve the problem. Beyond it, there is a wall, and on this wall there are unknown induced charges. It is a metallic wall, so I do not know what charges there are. However, I could say that I know that at this point I have grounded the wall. So, I know x of 0, but I do not know x dot of 0, or I do not know del phi del x. Knowing del phi del x at this point means that I know the amount of charge that is sitting on the wall at that point, but I do not know that. What I happen to know is that if I go 1.5 meters down, I will hit the wall again, and at that point phi is again 0. So, the kind of problem I am trying to solve is not this kind of problem, it is in fact this kind of problem, which is d squared x dt squared plus k squared x equals 0, x of 0 equals 0, x of 1 equals say 5. That is, I am saying I have this equation governing my behavior. At 0 I am 0, at 5 I am some value. Now find the proper combination of A and B, so that I go from here to there. Now, this is a very standard problem, and I expect you to be able to solve it already. If you are not able to solve it, go back to your maths books, because this is not the course in which to teach you solution of ordinary differential equations. The solution of partial differential equations we will go into, but only in a little bit, because this is not meant to handle, this course is not meant to handle very detailed problems, but ordinary differential equations you should know. You have covered it in your first year curriculum. So, all you have to do is you have to find A times sin kt plus B times cos kt evaluated at t equals 0 and evaluated at t equals 1, and so you will get a matrix equation, trivial matrix one, which you can solve by inspection. Now, exactly the same kind of problem has to be done for Poisson's equation. But there is a question here. The question is, supposing I have this cavity, I have some charges. So, I say I have rho of x, y, z in V, and I say wall is grounded. Does this problem have a solution? Does it have one solution, or does it have many solutions? After all, I am not saying how the charges on the wall are distributed. Could it be that by distributing the charges on the walls differently, I will get different kinds of solutions? The theory is actually quite easy, but I will rather state the answer. Answer is that phi of x, y, z in V is unique meaning that there is only one solution, provided phi or del phi del n is specified at every point on wall. It is a very powerful statement. It says that I can say the top part of this wall is at 2 volts. I can say the remaining part, 1/3 of it, is at 0 volts, and the last part, by some method, del phi del n equals 0. The theorem says that if you give me such a wall, there is one and only one solution you can get out of it. Now, this is interesting as a theorem, but what is much more interesting is, by using this theorem we can find ways of solving quite a few problems, and I want to show you one of the problems. It is again one of those problems that you would have done in school, but you would have done it without knowing why it worked. supposing I have a large plate which I have grounded, and I put a charge q above that plate at a height d. Now, this is a problem that where I have specified the potential on this surface, and potential anyway goes to 0 at infinity. So, I know all the charge inside the cavity, and I know the potential on the cavity wall. So, I should be able to solve this. There is exactly one solution that satisfies all these conditions. But which solution is it? Well, what I do is I do a trick. I say there is nothing said about what is here below this plate. It could be anything. So, I can put anything I like, and if I put it and get the correct answer, that answer also must be correct, because there is only one correct answer. Howsoever I get that correct answer is okay. So, what do? I put a charge minus q the same distance below the plate as the original charge was above the plate. And why do I do this? I do this because I know that if I take any point on the plate, it is equidistant to both these locations. So, there will be an electric field that will point towards this charge, there will be an electric field pointing away from this charge, and if I combine these two, I get a field pointing straight down, which means it is a constant potential surface. I will complete this example next time, but read up your textbook and understand method of images.